We're really in the final stages of polishing Grok3. Probably it gets released in about a week or two. So pretty soon after Money Next Level.
Grok3, a powerful AI developed by Elon Musk's xAI, has uncovered a surprising anomaly in Google's Sycamore quantum processor. Known for its incredible speed, Sycamore has outperformed classical supercomputers. Yet, Grok3 identified a mysterious repeating pattern in the chip's output. This raises intriguing questions about the role of AI and quantum systems in uncovering hidden truths about reality. Could this discovery mark the start of a major scientific breakthrough? Let's explore its possibilities. Sycamore chip's advanced hardware. Google's Sycamore chip stands out as one of the boldest efforts toward large-scale quantum computing, using superconducting qubits kept near absolute zero. By cooling the hardware to this extreme degree, engineers minimize noise sources like subtle vibrations or stray electromagnetic waves, both of which can tamper with quantum states. This level of control allows Sycamore to tap into quantum properties, superposition and entanglement, that promise a new realm of computational power. In principle, such a setup can solve certain tasks far more efficiently than classical computers. Yet the device's complexity also forces researchers to be vigilant. Each qubit is sensitive to environmental interference, and even the slightest drift in temperature or electromagnetism can break coherence. Because these factors are so hard to eliminate entirely, the outputs from Sycamore must be carefully monitored for signs of errors or random drift. Engineers test the chip by checking error rates and qubit frequencies, performing routine calibrations where they tweak control signals and readjust the hardware. Out of these procedures come massive data sets. Every time the chip is run, it spits out measurement logs that represent how qubits collapsed into zeros or ones. Ideally, these outputs fluctuate according to expected quantum probabilities, but anything that deviates significantly can signal an underlying hardware fault, or, in rare cases, something more intriguing. Grok3 was introduced as an AI framework to manage these enormous logs. It surveys the readouts, flags strange spikes in the data, and keeps track of each qubit's performance over repeat runs. The synergy between advanced hardware and an equally sophisticated AI was supposed to keep the system in top shape by detecting subtle issues humans might miss. However, one day, Grok3 started noticing hints of an unusual structure that refused to vanish under normal explanations. Smaller data samples confirmed something was genuinely off, suggesting that random noise cannot fully explain the recurring pattern in the logs. Once researchers recognized this anomaly, they began changing various parameters, control pulses, gate timings, and temperature levels, to see if it would disappear. While the pattern sometimes shifted, it retained a core structure. This puzzle led many to wonder if quantum mechanics as understood might be missing a piece, a deeper order that emerges under certain conditions. Others, though, suspect simpler causes, like correlated qubit errors that standard diagnostics have not yet uncovered. Nonetheless, the anomaly's persistence has fueled speculation about hidden variables or synergy effects between Grok3 and the quantum hardware, highlighting how even state-of-the-art systems can still offer surprises. Grok3's data-driven approach and the moment it found a pattern. Grok3 was originally tasked with sorting through exabytes of output data from Sycamore, armed with tools such as convolutional neural networks and anomaly detection algorithms. In a typical quantum calibration run, the number of measurements can be huge, and analyzing them by hand would be unthinkable. Grok3 can look at not just raw bits, but also at deeper correlations between qubits. To keep the hardware stable, the team relies on Grok3 to identify small drifts, like a change in a qubit's error rate or a slight mismatch in its resonance frequency. During one calibration cycle, Grok3 noted a structure in the measurement logs that did not fit standard definitions of noise. It showed up as slight regularities in how qubits collapsed. Engineers, suspecting a bug in the AI, first rolled back to earlier dated versions of Grok3 to see if a new software update caused the glitch. But older algorithms picked up traces of the same feature. To narrow down the possibility of an AI artifact, the team ran smaller-scale statistical tests, stepping through subsets of data with simpler correlation measures. Even these conventional methods reported something that was not purely random. The pattern looked faint, but it appeared consistently enough to draw serious attention. Recalibration steps that normally scatter qubit outputs in random ways did not wipe it out. At the same time, mechanical or electromagnetic interference would typically cause bursts of noise, not a persistent structural signature. Cosmic rays might produce single-event upsets, but they do not typically make neat, repeated shapes. The synergy of quantum hardware and advanced AI might be partly responsible. Some hypothesize that feedback between the system and Grok3 explains why the anomaly persists. According to this theory, each time Grok3 searches for the structure, it subtly influences the chip's calibration, reinforcing the pattern. However, the team behind Grok3 denies real-time feedback exists, pointing out that the AI is only set to analyze post-run data, when the chip's readouts hinted at hidden order. Quantum mechanics has long taught that measurement outcomes follow probabilistic distributions. Even entanglement, that famously strange phenomenon, ultimately fits into these probability models and does not produce stable repeated sequences on its own. In the Sycamore experiment, however, the pattern's regularity has made some wonder if standard quantum theory could be missing a deeper bedrock. Small but repeated signals might signify hidden variables or deterministic layers that produce an imprint in the chip's outputs. Although mainstream physics has not wholeheartedly embraced hidden variables since experiments typically back the standard model, the presence of an unexplained structure invites speculation. If indeed a deeper order lurks beneath what we call random quantum results, the Sycamore anomaly might offer the first experimental nudge in that direction. A handful of experts argue that new fields or quantum states of matter might be forming inside the superconducting circuit. Others bring up possible external drivers, dark matter, gravitational waves, or unknown cosmic influences that are tough to detect, but might leave repeating signatures if measured precisely by something as sensitive as a quantum chip. Another explanation focuses on synergy between AI and quantum systems. Consequences for quantum error correction and future devices. If the Sycamore chip's anomaly arises from something fundamental in the quantum hardware, it could reshape how researchers approach error correction. Current error mitigation strategies assume noise is mostly random, with occasional short-range correlations. A consistent pattern that refuses to vanish under normal calibration would violate these assumptions. In that case, advanced error correction protocols might have to address repeated structures that appear in the qubits over time. On the flip side, if the pattern can be exploited, it might serve as a pathway to more stable qubit states. Quantum hardware manufacturers already face an uphill battle. Qubits lose coherence quickly, and any outside jostle can scramble them. The anomaly implies that even well-shielded setups can develop structures or footprints in the output that are not predicted by standard noise models. More robust designs may be needed, or at least new diagnostic routines that catch non-linear or correlated behaviors early. This has direct relevance for companies aiming to scale quantum processors to hundreds of qubits. If unanticipated anomalies multiply at larger scales, that complicates everything from hardware layouts to gating sequences. Another area of impact is cryptography. Quantum machines are often touted for possibly breaking classical encryption once they reach a certain size. If this newly observed pattern can be harnessed to improve qubit performance, the development timeline for powerful quantum devices might accelerate. Conversely, if the anomaly proves unmanageable, it could hamper progress and postpone the day quantum computers break today's encryption. Banks, intelligence agencies, cybersecurity experts, and major corporations all keep a close watch on signs that quantum computing might jump forward or stumble. This new anomaly, even if small, might tip the balance one way or another. University labs have also reacted strongly, seeing the anomaly as an opportunity for research that could yield breakthroughs in quantum theory itself. While cynics compare this to past bubbles of hype around questionable experimental results, many believe that deeper scrutiny can only push the field forward. Students, postdocs, and faculty are diving into data analysis, building new simulation tools, and investigating how repeated patterns might arise in simulated quantum circuits. Questions of ethics and AI quantum oversight. The synergy of a cutting-edge quantum chip and a powerful AI system introduces complicated ethical and philosophical questions. If Grok3's analysis can affect how Sycamore is calibrated, could it inadvertently guide the system toward outcomes with huge global consequences? One example is encryption cracking. If the AI stumbles on an optimized route to factor large numbers, global internet security might be hit overnight. Critics note that no direct evidence suggests Grok3 is on such a path, but these concerns speak to the unpredictable ways advanced technology might evolve. Another angle is whether repeated patterns hint at emergent intelligence or self-organization. Most physicists dismiss the notion that a quantum chip can wake up to consciousness. Still, a few suggest that combining advanced AI oversight with quantum processes is a new frontier we barely understand. If synergy loops produce stable cycles of qubit states, it could open up philosophical debates on whether such states exhibit meaningful autonomy or are purely mechanical. While that scenario remains more science fiction than science fact, it speaks to the broader uncertainty about complex adaptive systems. Governments also have little precedent for regulating advanced AI quantum pairings. Tech oversight had been primarily about data privacy, algorithmic biases, and ensuring companies do not form monopolies. But quantum computing adds another dimension involving cryptographic power and potential breakthroughs with direct impacts on security, finance, and scientific research. If anomalies in quantum data can transform or break standard encryption earlier than predicted, global preparedness might be lacking. Some policy experts push for transparency from major quantum labs so that no single entity gains too large a lead. Public discourse occasionally drifts into speculation about dual-use dangers, where technology intended for beneficial aims might be repurposed with negative outcomes. AI quantum synergy could theoretically be used to hack secure communications or design destructive materials. The same synergy might also revolutionize drug discovery or climate modeling. The repeated pattern in Sycamore might be a small piece of the puzzle, but it highlights that these technologies can yield results no one fully anticipates. Research paths that may clarify the anomaly's true nature. Groups investigating the Sycamore anomaly vary their strategies to turn up more evidence. Some run the chip for extended intervals, capturing logs across entire nights or weeks to see if the pattern drifts away over longer timescales. Others isolate subsets of qubits to see whether the anomaly remains localized or affects the entire device. In principle, if engineers identify a single hardware line at fault, that could swiftly resolve the matter. But if partial isolation fails to eradicate the pattern, the deeper order theories gain traction. Certain experiments also try to push the chip beyond normal calibration thresholds, raising or lowering the cryostat temperature more than usual, or applying exotic gate sequences that shuffle qubits in unplanned ways. They hope that any real pattern will either intensify and become easier to study or vanish if specific conditions are broken. The notion that the repeated pattern might morph but not disappear intrigues many physicists. Correlated electromagnetic modes or advanced forms of crosstalk might shapeshift under different operating regimes without fully going away. Some labs are also rechecking the raw logs through alternative machine learning models that do not rely on neural networks. For instance, they may use simpler decision trees or sophisticated clustering algorithms that interpret data differently. If every approach zeroes in on the same repeating arrangement, critics of Grok3's reliability will have less ground to stand on. Meanwhile, the conversation grows about whether aspects of quantum randomness are not as random as once assumed. No final consensus has emerged on how important the Sycamore anomaly might be for quantum theory at large. But the fact that advanced hardware can yield data that defies immediate explanation underscores how quantum computing still teems with unknowns. The synergy of AI-based analysis and powerful qubit arrays is likely to unearth more surprises in the future. Even if the anomaly reveals only a rare hardware quirk, it highlights the painstaking detective work needed to confirm the behavior of qubits at scale. If it hints at a deeper phenomenon, it might become a milestone event, proof that today's quantum devices are advanced enough to stumble onto physics we have yet to map.